All right, so now I'm going to speak for a bit about mid-ocean ridges. I'm going to try and speak slower than in the first section, so sorry about that. Okay, why start with mid-ocean ridges? Might seem a bit exotic being out in the ocean, but these are basically the simplest example of mantle melting and crystallization on Earth. The reason for this is it is adiabatic decompression melting in normal temperature mantle. There's very few complicating factors. We don't have this big, stack of continental crust on top. We don't really have wet melting. It's pretty straightforward. All right. So we'll start with what are mid-ocean ridges. The mid-ocean ridge system is a continuous ridge of underwater mountains or ridges in the deep ocean. When I say deep, the water depth is generally more than 1,500 meters. There are very few places on Earth where it gets much shallower than that. Iceland is one example, but that's a bit complicated because there's a mid-ocean ridge and a plume. So in general, they're very deep. I think there's about, you see, between 40 or 60,000 kilometers of mid-ocean ridge. And on this map at the bottom, you can see that the crust is actually color-coded by its age. So we can see down the ridges, which are locally higher than the crust around them, the crust is very, very young. And as we get further away from the ridge, it's older.
Question?
Yes?
So how do you measure that? Is that just from the foot of the mountain to the top? Or?
Yeah, sorry, that's just water depth. So the actual old bits of oceanic crust here are generally about 4,000 meters deep, and the ridge is about 1,500. So there's about 2,500 meter drop off between the ridge and the base of the oceans there. Yep.
So the gray parts of the ocean, that's because it's actually continental crust, or is it?
Yeah, that's a really good question, actually. Yeah, these are continental shelves, so very, very thin, or more thin continental crust, but not actually ocean.
Okay.
All right. Hopefully, when we talk about what oceanic crust looks like, you'll see why we're making that distinction, not just based on whether it's covered in water or not. Okay. It's important to note that not all ridges spread at the same rate. So essentially, two things control it. One is the plate velocity, the speed that it's moving at, and the other one is the distance from the pole of rotation. So because we're moving on a sphere, we're not just moving flat, straight, forward, backwards, left, right. The motion is actually a rotation around a pole of rotation. And so you can kind of like visualize this here. The Pacific plate is moving as a single chunk, right? But it's not all the spreading rates are the same. So they're quite slow up here and they're very fast around here. It's because it's rotating. So it'd be a bit like, opening up kind of a wedge. But I wouldn't worry too much about this. Why it's happening, the biggest thing is to know that there are, broadly we can categorize them into fast, medium, and slow ridges at different speeds. Okay. If we zoom in a bit, mid-ocean ridges are made up of what we call ridge segments, and they're separated by these transform or strike-slip faults. And these transform faults are again to do with the geometry of moving on a sphere. Yes? So the transform fault is the actual fault that's making the motion, and then these leave behind these fracture zones. So let's see if we go back to this slide here. You can actually see these. That's a big transform fault, right? The ridge is coming down here, and then there's a big step, and then it carries on, and then it leaves these fracture zones that you can kind of see curving off. Okay. Oceanic crust, as I mentioned briefly before, it's very, very young at the ridge center, and it becomes older away from the mid-ocean ridges. Probably the most like obvious and basic way we can see this is that the sediments get thicker away from the mid-ocean ridge. So if you go to the ridge itself, there's virtually no sediment. As you move away, there's more and more sediment. That means it's been depositing for longer. We can also see it with these magnetic reversals that I don't know if you would have covered in some of your other courses. Okay. So essentially the Earth's magnetic field, its polarity flips every so often. So right now, the North Pole is in the north, because that's why we called it a North Pole. But maybe every few 100,000 years or so, it flips so that if your compass was here after a magnetic reversal, north would point towards the South Pole. So what that does is, as we're making new oceanic crust, magnetic minerals actually line up in the direction of the magnetic field. So we can basically see whether the magnetic field is pointing north or south. And with these systematic flips, and they're symmetrical, we can tell that the crust is getting older as it moves away. We can correlate these magnetic reversals to other ways of dating and get this kind of magnetic timescale. All right, so this is telling us that we're making oceanic crust at these ridges. Evidence for volcanic activity at mid-ocean ridges. Probably one of the obvious ones would be pillow lavas, pillow basalt, and I think Todd had showed you a video of these forming before, so hopefully you're aware of them. So these are fresh-ish, well, these are new basaltic volcanic rocks forming at the ridge. We can also see loads of evidence of hydrothermal circulation, so there's a lot of heat flow. This produces these things called black smokers, or kind of chimneys. And what's happening there is water is getting into the crust, it's being heated, it's stripping a bunch of crap out of the oceanic crust, and it's getting spewed out of a vent. And when it gets spewed out of the vent, it cools, it starts crystallizing minerals around the vent, which builds up a chimney, and it lets off this big black plume into the water column. And then recently, we've actually seen, and let's hope the link works, we've actually seen volcanic eruptions at mid-ocean ridges. So, don't think this will come with sound, but hopefully we can watch the actual eruption. Oh, didn't expect that. So that is basalt lava erupting, depth of 1,500 meters. It's being filmed from a submersible.
Bright red, these big bursting bubbles, these exposed vents of volcanic gases pouring out, exposing the molten red lava, these little sort of fountains, if you will, and just suddenly the Earth's crust cracks open and out pours red hot lava. What we can see is the magmatic gas somehow or another manages to fall behind the magma, creates these slugs of gas, potentially, that push up beneath the magma and pushes it out, kind of like a bubble gum, bubble gum bubble.
All right. So that was some amazing commentary. But I think that's pretty cool that we can actually watch these things. Yeah. So for a long time, we knew there was volcanism down in these ridges. We could see all the basalts, but it's actually, you have to be kind of lucky to know when it's going to happen, right? You have to have a submersible down, you have to have a camera in place. Like, that's not... Okay. So just to summarize that, mid-ocean ridges are divergent margins. They have active volcanism, and we're creating new oceanic crust there. There's a continuous system that spreads over most of the world's oceans, and they're made up of ridge segments separated by transform faults. Was that everyone on board? Any questions? Good. All right, we'll get into some more details now and talk about upper mantle and mid-ocean ridge structure.
Just one question.
Go ahead. Yes.
How does the magnetic field and mid-ocean ridges have anything to do?
Oh, so the mid-ocean, the magnetic field there is just giving us a timer showing that this crust is getting younger. It's not actually influencing the melting or anything in the mid-ocean ridge, but when you make a basalt, some of the minerals you crystallize are magnetic, and these orientate themselves towards the magnetic field. So basically, you'll have some basalts, if they're recent, like really recent, then they'll all be pointing to the North Pole, all those little magnetic minerals. If they're a little bit older, from last time the magnetic field was reversed, they'll all be pointing to the South Pole. So if you drive a ship over a mid-ocean ridge with a magnetometer, you can get these stripes of up, down, up, down, up, down, and those are the steps of these little ages. What's the best way to describe that? Yeah, this is just the first little bit formed when the magnetic field was pointing north, and then it kept on spreading, and the magnetic field flipped, so you'll have a band all pointing south, and then as it keeps spreading, the magnetic field flips, they'll be pointing north again, and so we can get an idea that it's getting older as we go away from the ridge there.
Okay, so that picture with all the stripes on, just like normally zones where the compass kind of freaks out?
It's not like it freaks out. It's like if we measure the magnetic field very, very sensitively, we can see that there's magnetic minerals like pointing in a certain direction there.
Oh.
So, you know, these are all being measured at the present day. So the magnetic field is still north on the whole, but we can measure these little changes of which direction the magnetic minerals are pointing in the oceanic crust.
Mm. Mm. Yeah.
I hope that's...
Like the minerals kind of...
Yeah. You can do this on rocks on land as well. It's just in the oceanic crust, because we have this continuous magnetism as it's spreading, then you get this really nice record of like every time the magnetic field flipped. And maybe we know from like comparing it to other geochronology or fossils, we might know that there was a period in the Miocene where the magnetic field was pointing south for 100,000 years and then north for 700,000 years. So then we'd expect to see a big thick north stripe and a little thin south stripe.
Yeah,
Yeah.
I understand. So, like, depending on what direction it's like going, you know what age it is.
Yeah, or more by the pattern of the stripes. Right. If you just measure one rock and it's pointing south, you don't know if it's the last time it was pointing south or the time before that or the time before that. But if you measure across a wide area, you can see these reversals, and they happen systematically, and they're the same all over the planet. So we can we can figure out the age.
Yeah.
Yeah. Okay. Great. Yeah. So hopefully you know this from first year. We can divide the upper mantle into the lithosphere and the asthenosphere. The lithosphere is basically the rigid plates. When we talk about plate tectonics, the lithosphere is what makes up these plates. And so it is the crust and it's the uppermost mantle, and this is the bit that behaves rigidly. So basically, when one part of the Pacific moves in one direction, the whole Pacific plate is moving, right? The asthenosphere is the bit beneath the lithosphere, and it's also upper mantle, but it's convecting. It's really, really important to stress that the asthenosphere is also solid. It's convecting by something we call solid state creep. All right. When it comes to composition, both the lithospheric mantle and asthenospheric mantle are broadly the same composition. There are some differences that we'll talk about in a sec, but these are basically mantle peridotites. So the main difference is whether they're rigid or not. All right. You'll see different definitions of lithosphere. I think for the mid-ocean ridges, we're mainly going to be talking about this thermal lithosphere. But basically, it comes down to what makes something rigid, right? So one way is if it's cold. So if we look at the thermal lithosphere, next to a mid-ocean ridge, the lithosphere is really thin. And that's because the plates are moving apart. It means the asthenosphere can upwell really, really close to the surface. And because it rises adiabatically, again, it's not losing heat to conduction because it's rising faster than it can cool down. Then we basically get really, really hot stuff. This is 1300 degree C, a line of constant temperature. we can have really high temperatures right underneath the mid-ocean ridge. So the thermal lithosphere is very thin there. Another one would be the chemical lithosphere, and this is because when we remove melt, we change the composition. This can also make it more rigid. Kind of a key thing here would be that if you have water in mantle rocks, it makes them a bit more plastic. They're still solid, but they can deform a bit easier. So chemical lithosphere would be everything that's had melt removed, and so this is going to be at a constant depth from the ridge. And then the last definition is we can talk about a mechanical lithosphere. The idea would be whether it's rigid or not. And so this is going to be some combination of how cold it is and what the composition is. Right. What I've plotted here is this is viscosity. So this is how thick it is. So like honey is more viscous than water. It's thicker. It flows more slowly. Basically, at the top, it's incredibly viscous, so it's not really able to flow, so it's behaving rigidly. And as we go down and it gets hotter, we can see that it actually gets less viscous, so it's weaker, it's more able to flow. And then down in the asthenosphere, it's solid, but on long time scales, it's weak enough to flow. Just to try and explain this a little bit more. When I say a solid's able to flow, it's not a liquid, but what's happening is there's all these little defects in the crystals and along grain boundaries, and as there is pressure or stress on it, these defects can basically jump and the crystals can rearrange themselves, and over time that means that they can actually move very slowly. I've put this analogy to the pitch drop experiment. So this is a relatively famous science experiment where someone, I think it's about 150 years ago, just stuck a bunch of pitch or tar, like a kind of very thick oil. They just stuck it in a funnel and left it. Now, if you look at it on a short time scale, it's totally solid. But over 150 years, this has actually dripped. So if you were to poke it, it would be solid. But in 150 years, it's dropped like 2 or 3 times or something. So it's flowing, but incredibly slowly. And this is the same thing that's happening in the mantle. We won't worry about this too much, but yeah, the viscosity of mantle asthenosphere is really high. It's similar to piano wire. So if you imagine the wires on your piano, it feels really solid, right? The only reason it's able to flow is because the mantle is huge, and we're talking about geological time. So basically, how much something can convect is related to the thickness of the layer cubed. So when you have a 3,000 kilometer thick mantle, it can still convect, even though it's solid and it's really viscous. All right, any questions? Because I know this is...
Is it still crystalline?
Yeah, it is.
It is.
Yeah. So I mean, you got to imagine it as let's say this is an olivine crystal in mantle. It's got a defect, and this defect is going to move along really slowly, and maybe after 1,000 years, your olivine crystal is like a few millimeters to the side of where it was. This is the sort. It's incredibly slow, but it is convecting, and it's confusingly it's convecting quite vigorously because it's so deep. We have these vigorous convection cells. So very slow, but yeah. I feel like there's going to be more questions on that bit. Does anyone have anything else they want to? Leonard, maybe? Yeah?
Why is it called creep?
I guess it's creeping along slowly. Yeah.
Is that, okay,
Yeah. Technical term. Genuinely, it's not, yeah. Not creep in the Radiohead sense. Okay, loudest.
Convection, is that, I think we learned that earlier, like the heat going up and then going around. Is that this?
Yeah, yes. So convection is just in anything that's behaving as a fluid. It is movement of the fluid because of heat. And generally on Earth, if you're heating something from the bottom, it rises, then it cools off at the top, and then it sinks. So that's a convection cell. So convection could be in hydrothermal circulation, where you've got seawater going into mid-ocean ridge, getting heated, and then then it becomes less dense and moves up. Happens in the mantle because you're heating from the bottom with the core mantle boundary.
And that convection makes the creep, or is that the thing that drives the creep?
Yeah, it's a couple of things. So, yeah, mantle convection is quite complicated, but on Earth, the main thing that's driving convection is actually subduction. So even though the plate that's subducting is solid, it's a form of convection because cold stuff's going down. And if something's going down, something has to be coming up. Aside from that overall kind of pattern, we probably have like smaller scale convection cells, and then we've got mantle plumes. So if subduction zones are sinking into the lower mantle, something has to come up. That's generally going to happen at the areas where it's hottest. This is going to be a mantle plume rising. So, yeah. So the creep, yeah, the movement is overall in response to these various convection processes. Yeah.
What is an imperfection in the
Oh, yeah. So this, you probably learned in mineralogy, you have all these like perfect lattices and stuff. Sorry?
No, nothing.
Yeah. So you learn about all these crystal structures, and in the models that you look at, everything's always perfect, right? But sometimes there's a gap. You know, you might just be missing an ion. Sometimes there might be a trace element in there. And if it's got a different charge or something, or a different size, it distorts the structure. And so these could be imperfections, defects.
Creep faster if the mineral is imperfect.
Good question. Probably, yeah. But I don't know enough about this stuff. Yeah. Yeah.
You had the viscosity, but then you also said something about the elasticity.
Yeah, actually, I reused this slide from an older lecture that was aimed at fourth years, and then I decided it wasn't a good idea to talk about it. But basically, if there's earthquakes, on a short time scale, it's behaving elastically, right? It's behaving like a solid, because you need that for it to break. But what's confusing here is it depends on the time scale. So, for example, something could break in an earthquake if the stress is high, if it's being forced on a short time scale, but on a longer time scale, it could flow. So this is like this pitch drop again, right? Like if I were to grab the bottom of this, I could snap it off. If I stress it quickly, it'll act like a solid. But if you just leave it there for 150 years, it flows. Okay. I think that's enough on creep, because, yeah. Okay. So going back to the mid-ocean ridge structure, and this diagram's from Wikipedia, proving that you can get good stuff from there. As the plates are diverging, we're having this passive upwelling. So plates are moving apart, mantle is moving up in response to that, because you can't have a gap. Oh yeah, I said that. So there's no force like pushing the mantle upwards, it's just being pulled up because the plates are moving apart. Beneath the ridge axis, because the plates are being pulled apart, you have effectively no lithosphere, or it's very, very thin. What is then happening, because this mantle is moving up, it's depressurizing. We talked about it before, that's one of the main ways that you get melting in the mantle. It melts, those melts go on to form oceanic crust, and we leave this depleted mantle behind. This mantle is being pulled sideways because the plates are moving apart, and it cools as it goes away from the ridge. And this is our thermal lithosphere, right? And it gets thicker as the plate cools over time. We'll talk a lot more about oceanic crustal structure in the next hour. But basically, these melts from the mantle rise into the crust, and they form this kind of characteristic stratigraphy of oceanic crust. So at the top, we get pillow basalts, which we already saw at the ridge. Underneath that, you get a sheeted dike complex. This is basically, as it's pulling apart, you're getting dikes intruding upwards. It keeps pulling apart, another dike intrudes upwards, and another intrudes upwards, and we get a bunch of parallel dikes. Beneath that, so here you can see these yellow bits are the volcanics, these are pillow basalt. We have our sheeted dikes. We maybe have some other later melts that cross-cut through the sheeted dike, don't worry about that too much. And then underneath we have this huge zone of lower crustal cumulates, Here it's shown as a mush because this is supposed to be, this is supposed to be a snapshot of when it's happening at a mid-ocean ridge. So mush is just like a mix of crystals and magma. And then once these all crystallize, they become gabbros. You can see this, it's an older diagram, but I think it shows it really nicely. So at the top of the oceanic crust, we might have some sediments that are formed. Below that, pillow basalt. Below that, this sheeted dike complex. And below that, these mafic cumulates. So gabbros is the main one. You can ignore the diagrams there. Underneath that, we have ultramafic cumulates. So here it's shown as pyroxenite and dunite. Pyroxenite is a rock that's mainly pyroxene. Dunite is a rock that's mainly olivine. Sometimes we'll get something called troctolite, which is olivine and plagioclase. So these are ultramafic cumulates. And underneath all that, there's mantle rocks. Okay. So the main points there is that the lithosphere are these rigid plates. They comprise the crust and the uppermost part of the mantle, the bit that is more solid, more rigid. The asthenosphere underneath is also solid, but it convects. It is flowing very, very slowly. It is not behaving rigidly. At the mid-ocean ridge, the fact that the plates are moving apart means that the lithosphere is very, very thin, and this asthenosphere can flow upwards, and it will melt. These melts make oceanic crust. Okay, so it's starting. Go ahead.
On that slide where you had the definitions of the lithosphere,
Yeah.
you had that chemical versus thermal graph.
Yeah.
You said something about the part where you don't have the temperature lines was because there was a mantle coming up and it rised faster than it could cool, or what was that? Why didn't the temperature gradient kind of continue through that chemical?
The thermal lithosphere, this is because it's hot all the way up. The chemical one corresponds to how much has had melt removed. So if you think about the mantle flows up and it starts melting, right? The more it flows up, the more it melts. But everything past this line where the melting starts has had melt removed. So actually then, even though it's really hot, this is still like chemically like the lithosphere. It's been a bit depleted.
And the thermal boundary is kind of where the plate boundary is. Like when you see the mid-ocean ridge, you can kind of see the plate thinning towards the top. That's kind of like that
exactly, yeah. So that's what people are using, like a thermal definition of the lithosphere. Because everything under the ridge is really hot, right? It's upwelled, it hasn't had enough chance to cool off. It's really hot, but it has melted. So if we're talking, I wouldn't worry too much about these different definitions, but in general, people when they draw mid-ocean ridges, are always talking about thermal lithosphere. And that's just down to the fact that when it's really hot, it's going to behave very weak. When it's cool, it's going to behave more rigid. Yeah. That's it.
Yeah, I was just wondering about the lower crust of fluids.
Yes.
How do they form?
Talk more about it in a bit.
Okay.
Yeah. Okay. Good. Okay. I think this is the last part of this lecture. We'll talk about mantle melting at mid-ocean ridges. All right. I wanted to start off with what is actually melting. So overall, it's mainly mantle peridotite, and this is an ultramafic rock. It's technically a metamorphic rock because it's sat there at really high temperature. It's not actually an igneous rock itself, right? And it's mainly made up of olivine. It varies a bit, but let's say 50 to 60%. Just put up the chemical formulas of each one. So olivine is generally really magnesium rich in the mantle, and there's a bit of magnesium, a bit of iron, a bit of silica. It's pretty simple. We also have orthoperoxene, which forms between 10 and 25% of mantle peridotites. And this is similar to olivine, but you'll probably remember that pyroxenes are these single chain minerals rather than having that isolated tetrahedra. So it has a bit more silicon compared to the amount of magnesium and iron. Clinoperoxene, we'll talk about clinoperoxene composition later, but in the mantle it's a diopside, about 10 to 20%. And this is some sort of calcium, magnesium, iron, and silicon. The last one is there's an aluminous mineral. So this just means it's got aluminium in it. And that's between 3 and 10%, and it varies with depth. What we can see here, these are basically all the major constituents of mantle peridotites: magnesium, iron, silicon, calcium, aluminium. So sometimes when people are doing like simple models of these, they'll talk about CMAS system: calcium, magnesium, aluminium, silicon. This is most of what's in there. All right, this aluminium-bearing mineral changes with depth or with pressure. So below about 20 kilometers depth, it's mainly plagioclase. This is kind of the full formula of it. In mantle peridotites, there's more calcium, so it's more anorthite. There's less sodium. Between about 20 and 70 kilometers, it is this mineral called spinel. That is a magnesium aluminium oxide. You might have heard in your mineralogy courses about spinel group. This is like sensu stricto, like this is strictly spinel, is the magnesium aluminium version. It is part of the spinel group. The spinel group is named after this mineral. Past about 70 kilometers depth, we get a garnet peridotite. And this garnet is mainly pyrope, so it's a magnesium-rich garnet. And so that was these beautiful garnets in the garnet peridotite photo that I keep reusing. At mid-ocean ridges, most of the melting is happening in the spinel field. And there's just a little bit of garnet field melting, yes.
Why do you call them metamorphic rocks?
So an igneous rock is something that's crystallized from a magma, right? So, I mean, I guess technically these crystallized maybe from the magma ocean like 4 billion years ago, but since then they've just been sat there at high temperature. And they've been melted, and they've had melts added, and they've had all sorts of crap happen to them, but they're not, cumulates from a igneous, from a magma. Okay. Is that a question, Oscar?
Kind of. So
Yeah.
How they end up forming is that because of like recrystallization. So end up the olivine stuff that drops out and sits on the bottom, whatever, and you get that, like when we saw earlier.
No, that's what I'm saying. These are metamorphic rocks. These have been solid for, some of them. That, if you think about it, every mantle peridotite at some point, because of subduction and mid-ocean ridge spreading and melting, they've probably had melts removed. Some of them might have got incorporated into oceanic lithosphere, subducted again, brought back closer to the surface. These things have had this incredibly long and complicated history. We can see that if we do geochronology on these things. Going back to my rhenium osmium that I said I wouldn't talk about. When you go take like mid-ocean ridge peridotites, and you'll find some that are like 2 billion years old, just sat there. So yeah, they're metamorphic rocks. Okay. Good. Okay. So the starting composition before we melt stuff in a mid-ocean ridge is pretty much fertile lertzolite. And when we say fertile, we just mean that it's not been melted a lot. So when they say fertile, it's fertile for producing melt. It's basically not been melted. So it's easy to melt. And when we melt it, as I said before, the partial melting, you're not melting all of it 100%. So you're changing the composition. You'll sometimes see this referred to as non-modal melting or incongruent melting. And what's happening there is not all minerals are melting by the same amount, so they're not all contributing to the melt equally. Very broadly, clinoproxene melts faster at first. So this diagram here is for classifying ultramafic rocks. I don't tend to use it much. It's a bit of stamp collecting, to be honest. But basically, 3 corners: orthoproxene, clinoproxene, olivine. If we have pure olivine, it's a dunite. If we have pure pyroxenes, these are these pyroxenites. That's referred to as a websterite if it's a mix between. Mantle rocks are basically lertzolites, and if they're fertile, they're kind of sat up here. Because clinoproxene melts faster, then we actually start to remove the clinoproxene, and we end up on this join between olivine and orthoproxene. So this is a hot spaghetti. So peridotites that have had melt removed would would generally be Harzbergite. So this is a depleted peridotite. If you have really extreme melting, you can get to a dunite, but it's not the way that we form most dunites. Most of them are formed by melt rock reactions that we'll talk about a bit more later. Okay, so starting with fertile lertzolite, melting, mainly removing clinopyroxene, ending up with a Harzbergite. And this is what I promised we'd talk about a bit more, is the adiabatic decompression melting. So what's happening is as the mantle is upwelling, it's actually cooling, right? Again, it's the same as the going up a mountain, air gets colder, pressure's getting lower. But the temperature change with pressure is less than the solidus is changing by. So the solidus is the temperature it melts at. So at higher pressures, the solidus is higher. At low pressures, the solidus is lower. And you can see the solidus is this line here. This is called the dry solidus because we're ignoring water from mid-ocean ridges. So as the mantle rises, even though it's getting colder, it actually hits the solidus at some point, and then it starts to melt. Now, we lose a bit of heat to melting, so it actually starts cooling down even faster. This is like latent heat of melting. But again, like melting your ice cube, it doesn't just melt, it takes some extra heat. So as we keep rising, the amount of melting actually increases, even though the temperature is dropping. Do you have anything else to say about this? Yeah. If we imagine that the mantle is at a higher temperature to begin with, then it would actually intercept the solidus at even higher pressure. And because it intersects the solidus deeper and it keeps rising, we actually get even higher degrees of melting. So normal mid-ocean ridges, this is the temperature, it's about 1300 degrees C. That means that the pressure at which it starts melting is about 2 gigapascals. That's similar to 60 kilometers depth. So we'd be in the spinel field there. In reality, we get a tiny bit of garnet field melting, but not much. Yes?
All these different pressure
Yep.
lines, are they should they be seen as one melt or different melts at different temperatures?
These pressure lines going across here,
Yeah.
this is like it's something they call the potential temperature of the mantle. It's just a way of reporting the temperature where we correct for that adiabatic cooling.
Okay,
So this would be a mid-ocean ridge.
Separate.
This would be a mid-ocean ridge where it's relatively cold. This would be a plume where it's really hot.
Yeah.
So each one of these lines is the path that an ascending blob of mantle would take. If it's normal temperature, if it's a little bit hotter, if it's really hot. Yeah. Does that make sense? All right. Melting at mid-ocean ridges, we have this kind of triangular melting region, it's called, and that is because of what we were seeing before, how the lithosphere gets thicker away from it. So basically, if we imagine plates moving apart, but there's also a mantle ascending at the same time, if you're a piece of mantle that's ascending over here, you move up a bit, and then after a certain point, the flow is mainly sideways. If you're ascending right beneath the ridge, you can actually move a really long way up before you get dragged sideways. So this makes this triangular melting region here, and you can see this kind of curve. It's similar to what we saw in the thermal lithosphere before. You can also see, because the stuff in the middle has ascended further, it actually gets to melt more, right? It's decompressed more. So this mantle that came up right underneath the ridge gets melted more than this mantle that came up to the side and got incorporated, got pulled sideways quickly. As soon as it stops moving upwards, it can't melt anymore, right? Because it's not decompressing. So we've produced the melt. Yes, so when you first make a melt, these things will be a very small amount of melt surrounded by solid. And they basically start to percolate upwards. This means that they're trickling up in between the grains. In some cases, they probably get aggregated into channels. So we have all these little trickles of melt, and maybe like streams joining a river, you get like a bigger channel, and you get a kind of focused zone of melt flow. So this is kind of a schematic diagram of it, where they all get focused towards the ridge axis. Yes. And so I've already mentioned this, but because mantle that made it close to the surface decompressed more, then the most depleted mantle is at the top, and the least depleted is at the bottom of the lithosphere. Yes?
So, did I understand it correct that these small parts of melt, they move up through a solid metal?
Yeah, you could think about it like, you know, like water moving through a sandstone, but with lower porosity. So because you've created melt everywhere, there's going to be this kind of like all these solid grains, and there's going to be melt along the boundaries between the grains. And because the melt is less dense, it starts moving upwards. Yeah. Yes?
Does anyone know why we get a triangular form? Just because how the viscosity or the...
It's to do with the geometry of this spreading. So if you think about it, so the lithosphere is really thin here, right? So I can upwell a really long way and melt and melt and melt, and then I'll get pulled sideways. I think it shows it really well in this diagram. But the lithosphere is quite thick here. So I only melt a little bit, and then I get pulled sideways. So the overall shape of that is triangular. Everything over here is no longer moving upwards, so it's not melting anymore. So the melting region is just this area where mantle is moving upwards. So it just comes about from the...
So it's also dependent on how the crust gets pulls on it onto this.
Weirdly, everything cancels out for mid-ocean ridges. So if you spread very quickly, the upwelling is faster and you get more melting.
Okay.
And if you spread very slowly, then the upwelling is slower. And so basically, it kind of cancels out. You end up with the same amount of oceanic crust unless it's super, super slow. And you end up with the same like net amount of melting. Because basically, if I'm moving fast, I'm melting faster, but I'm also getting out of the melting region faster. So it just kind of, it really neatly cancels out. So, yes. Okay. All right, so upper mantle is made of peridotite. Before it's melted, it's mainly this kind of fertile lertzolite. When it melts, you leave a depleted hartsbergite residue. At mid-ocean ridges, the melting is this adiabatic decompression melting, and it happens in a triangular melting region. The melts get focused towards the ridge axis, and we make oceanic crust. I think... Oh no, we've got a tiny little bit about making basalt. So did anyone have any questions on that section? I think conceptually this might be about as hard as it gets, so if you get this, it's all good. Yeah. All right, making basalt. I've called it part one because we don't just melt and make basalts, but we're going to talk about the melting in the mantle to make basalts. Okay. So as I mentioned before, the mantle melting is non-modal or incongruent. We're not melting everything in the same proportions. And so what that means is when we melt it, the melt is going to be a different composition to the initial mantle. The mantle is ultramafic, so it's got a crap load of magnesium in it, whereas basalts are mafic. So this is like a typical mid-ocean ridge basalt, maybe 8% MgO, compared to your fertile mantle peridotite with 38% MgO. So the very first melts that form what we call eutectic melts. So this is the lowest temperature melt that you can make that is in equilibrium with mantle peridotite. So thinking back to the adiabatic decompression diagram, we've just crossed the solidus, just started to melt. So this is a phase diagram. We'll do more about phase diagrams next week. But have you seen phase diagrams before? Yeah. So basically, this one is a forsterite, so that's olivine. Dioxide, that's our mantle clinopyroxene, and enstatite, this is kind of like mantle orthopyroxene. And if we plot lertzolite, which is lertzolit, because I stole it from a Danish person's slides, that's down close to the forsterite. And the eutectic melt, so this is the lowest temperature at which we can have melt that is in equilibrium with this, is up over here. So it's much closer to the dioxide and enstatite. So this is because more pyroxene is melting to make our basalt. All right? Yes?
What is non-modal?
The fact that we have four main minerals in there, right? And they're not all melting the same amount. So we're mainly melting clinopyroxene and the aluminous phase more at first. So then we get a melt that's richer in kind of clinopyroxene compositions. We're not melting a lot of olivine. So if we were mainly melting olivine, then the melt would be down here. Yes?
So melting the mantle will have more water polluting, and the salt will be more polluting.
Yeah, so before we went from lertzolite, which is olivine, orthoperoxene, clinoperoxene, and as we melt it, we go towards Harzbergites, it's olivine and orthoperoxene. So yeah, the residue has more olivine, more orthoperoxene, and the melt has kind of more of like a clinoperoxene composition. Yeah. Yes?
So it's called incongruent melting when it's melting non-modal.
Yeah, sorry, two words for the same thing, yeah. Non-modal is like literally this thing of like not all the minerals are contributing. Incongruent is this idea that there's a different composition, but yeah, basically these are the same thing. Yeah. Okay, don't think I had anything else to say there, so. Why are the melts less mafic than the mantle? We can just kind of think about this conceptually using a different phase diagram. This is a olivine binary phase diagram. Have you seen this before? Yeah, okay. So mantle olivine, it's about 4-stroke 89. So if we plot this here, it's up here. When it starts to melt, it's on the solidus, and we're at a fixed temperature, so we can just draw across and we can see this is the Mg number, the four-strike content of the liquid that's formed. So obviously mantle melting is more complicated than just olivine, but this is basically always true that the melts are always going to have lower magnesium than the solids that they're melting from. Yeah, so we can report this change using this this olivine Kd distribution coefficient. So the iron over magnesium in olivine divided by the iron over magnesium in the melt is about 0.3. So what this means is if we were to actually start melting this, we're removing liquids that have less magnesium and more iron. So if we were to keep heating this up, the composition of the olivine left behind would actually move up this way, and then it would be in equilibrium with the new melt over here. So if we melted it some more, then it would move up further this way, be in equilibrium with the new melt. The melt always has less magnesium than the olivine, except for the very, very last melt formed where we're melting pure forsterite. So conceptually, this is, again, it's not just olivine melting, but this is happening in all the mantle phases, right? As we melt dioxide, we're leaving behind more magnesium than iron. As we melt olivine, we're leaving behind more magnesium than iron. As we melt OPX, we're leaving behind more magnesium than iron. So this is why our melts are always going to have more iron, less magnesium. Okay, is everybody happy with that? There's two types of melting. These are like end members. Generally neither of them happen in reality. Most things are going to be some mix between them. But we'll talk about it a lot in this course, and those are fractional and batch melting. For batch melting, as we create a melt, it basically sits around in contact with the solid, and it's in equilibrium with the solid. This means it's able to keep exchanging elements back and forth, so that if I melt something 1%, then I melt it 20%. I never removed that 1% melt, it just hung around, and they can stay in equilibrium. Fractional melting is as soon as I form like a tiny bit of melt, so the second I cross the solidus, that melt is removed. So it flows off, it's gone. And so it's no longer in contact, it's no longer in chemical equilibrium with the solid. So we'll actually produce different types of melts based on whether we have fractional or batch melting. It's also possible to have intermediate scenarios. These are sometimes called dynamic or critical melting, and this is where some melt stays behind and some is removed. So this diagram kind of sums it up. If we have our solid source and we do batch melting, then we're left with a residual solid and a melt, and they sit around in contact with each other. If we have fractional melting, we make a residual solid, but we remove the melt really quickly, so it doesn't hang around. And dynamic or critical melting, we have residual solid with some melt trapped behind, most of the melt is I'm not going to talk about the different compositions these produce, but we'll revisit that when we talk about trace elements. So in the mantle, in reality, melting is pretty close to fractional. It's dynamic or critical melting. As soon as you make about 1% melt, because the melt is less dense than the solid, and it's basaltic, it's low viscosity, it migrates upwards. But there's always a little bit of melt that's trapped behind, because it can't fully get removed. These little melt increments, these percolate, so that's what we were talking about before, where it's flowing around the grain boundaries, they move upwards, and they will generally aggregate into channels, sort of like dikes. And if they make it into the crust, then they might end up mixing in magma chambers. So even though these little increments are formed, one might be the first 1% of melting, and one might be after much more decompression, it might be like the increment between 19 and 20% melting. These things, those melts will look quite different, right? Because they're formed from mantle that is progressively more depleted. But then they all get mixed together in magma chambers, and that smears away a lot of our compositional variation. Yep, and these, the kind of mixed or aggregate melts, these form the kind of precursor melts to what erupts at mid-ocean ridges. So these will often be referred to as parental melts, and like, they're the parents to the melt that we see at the surface. Okay, so just to summarize that, the mantle melts incongruently. We get mafic melts that have much lower MgO than the peridotites that we started with. The melting is pretty close to fractional melting. It's kind of this critical melting where as soon as you form a small volume of melt, most of it escapes upwards. And these melt increments mix together, and those make the parental melts to our mid-ocean ridge basalts. Does anyone have any questions about that? Yes?
I didn't understand what the batch melt is.
Yeah.
Fractional melt is when there's left behind, right? Of some of the minerals crystallizing, right?
So a batch melt, let's say I take my mantle and I start melting it, and I melt it by 20%. If it's a batch melt, there will be 80% solid left behind and 20% melt, but the melt is still in contact with the solid. If I do fractional melting and I melt at 20%, let's say I melt at 1% and the 1% goes. And I melt another 1% and that 1% goes. And I melt another 1% and that goes.
Okay.
So I'm doing these tiny little increments of melting, and the melt is rapidly being removed. Whereas batch, I'm just sitting there and melting it, and the melt fraction is increasing. So in reality, we don't get batch melting in the mantle, because the melts are less dense and they're low viscosity, so they migrate quickly. Yeah, batch melting is probably going to be a bit more relevant when we talk about granites, because granites are really viscous, right? So they're not able to just escape quickly along grain boundaries. You basically just sit there and melt and melt and melt and melt, and then you'll get like a big fat slug of granite. Yeah. Okay. I think that's it for this lecture, yeah. So I'll just leave that up. We can take another 10-minute break, because that was a lot. Yeah. And I'll see you back here at